Hey guys, today we are going to be reading this section in our textbook on winds, pages 46 to 52. We will start out here on page 46 down here. Have you ever flown a kite? Start by unwinding a few meters of string with the kite downwind from you. Have a friend hold the kite high overhead. Then, as your friend releases the kite, run directly into the wind. If you're lucky, the kite will start to rise. Once the kite is stable, you can unwind your string to let the wind lift the kite high in the sky. But what exactly is that wind that lifts the kite, and what causes it to blow? Excuse me, sorry about that. Well, understanding what wind is, I think we've done a good job in our last unit of explaining how it's really about air molecules, and that air molecules, if you have a air that is warmer, the molecules spread further apart, they become less dense and they rise. If they are colder, they become more condensed. They can when they become more condensed, they're more densely packed, and they can be denser and they will sink. And we're going to talk about some of those things in this section. Because air is a fluid, and a fluid means it's any substance basically that doesn't keep its shape. So that would be liquids and gases. So because air is a fluid, it can move easily from place to place. Differences in air pressure cause that air to move. A wind is the horizontal movement of air from an area of high pressure to an area of low pressure. The upward and downward movement of air is not wind, it is the horizontal, sideways movement. And winds are caused by differences in air pressure. And we're going to talk about what creates those differences. Most differences in air pressure are caused by the unequal heating of Earth's atmosphere. Convection currents, which we talked about when we talked about heat transfer, convection currents form when an area of Earth's surface is heated by the sun's rays. We had talked about how water and land heat up differently. And we said the land heats up faster than the water. It also cools faster. So, like it says here, air over the heated surface expands and becomes less dense. As the air becomes less dense, its air pressure decreases. So, as the air is warmed above the land, it becomes less dense, its air pressure decreases, and that air over the land will rise. If a nearby area is not heated as much, for example, a lake, the air above the less heated area will be cooler and denser. So we know that the air above the land will rise. We know that the air above the lake is cooler. The cooler, denser air with the higher pressure will flow underneath the warm, less dense air, forcing the warm air to rise. So what you essentially get is I'm grabbing my markers here. So essentially, when you get that land heating up, you have a body of water, and then maybe you have some land. As the land above as the air above the land rises over here, the air above the land will rise. The cooler, denser air will move in. Okay, that causes a current. So this air will rise. It will eventually cool and sink, and you get that convection current. Okay, does that make sense? I hope so. We're going to be talking about that, and I guess I could do a little more of a drawing here. So as the sun here heats the land and the water, the air above the land will become hotter and it will rise. The cooler, denser air from the water will move in, and that is our convection current. Okay. Measuring wind. Winds are measured and winds are described by their direction and speed. Wind direction is determined with the wind vane. That's this little drawing right here. Okay. The wind swings the vane so that one end points into the wind. The name of the wind tells you not the direction it's heading, but it tells you where the wind is coming from. For example, a south wind blows from the south towards the north. A north wind blows to the south. So if it is a south wind, it means it comes from the south, just like somebody of European descent came from Europe. It doesn't matter that they went maybe to China. They came from Europe, so they are European. So I kind of think about it that way, that a wind is named from where it comes from. Okay, so if it is a north wind, it is coming from the north heading south. Wind speed is measured with an anemometer. An anemometer has 3 or 4 cups mounted at the end of the spokes that spin on an axle, and the force of the wind causes the cups to turn. And I will show you an anemometer here. So an anemometer looks like this, and just a quick little video here. Okay, oh, wrong one. And it looks like this. Okay, that is an anemometer there, and that right there is our wind vane, pointing in the direction from where the wind is coming. Anemometer, wind vane. Okay, all right. So moving on, here we go. Wind chill factor, and we've talked about this a little bit. It says on a warm day, a cool breeze can be refreshing, but during the winter, that same breeze can make you feel uncomfortably cold. You know that, especially right now at this time of the year, the wind can be brutal. The wind blowing over your skin removes body heat. The stronger the wind, the colder you feel. The increased cooling a wind can cause is called the wind chill factor. Thus, a weather report may say the temperature outside is 20 degrees Fahrenheit, but with the wind speed of 30 miles per hour, the wind chill factor makes it feel like 1 degree above zero. We hear about it a lot here. We also talked about it today in our on our weather chart. We talked about it as the feels like temperature. Okay, there we go. Local winds. We have two different kinds of winds that we're going to talk about. We're going to talk about local winds and global winds. We're going to start with local winds. And local winds are a lot like our sea breeze and our land breeze that we've been talking about. Have you ever noticed a breeze at the beach on a hot summer day? Even if there's no wind inland, there may be a cool breeze blowing in from the water. This breeze is an example of a local wind. Local winds are winds that blow over short distances. And I know that you guys can see me moving here. Local winds are caused by the unequal heating of Earth's surface within a small area. They form only when large-scale winds are weak. We have two kinds of local wind. We have a sea breeze. Remember, winds are named from where they come. So a sea breeze would be a breeze that blows in off the sea or the lake. Unequal heating often occurs along the shore of a large body of water. It takes more energy to warm up that water than it does to warm up an equal area of land, which we remember from when we heated up the water and the sand in the beakers. As the sun heats up Earth's surface during the day, the land warms up faster than the water. And as a result, the air over the land becomes warmer than the air over the water. The warm air above the land expands and rises, creating low pressure. The cooler air blows inland from over the water and moves underneath the warm air, causing a sea breeze. A sea breeze or a lake breeze is a local wind that blows from an ocean or lake. And I have a little diagram here, I guess a big diagram. I'm going to show you. Here is our sea breeze. And you can see the land is heating up. The air above the land is rising, okay? Or the air above the land is becoming less dense, it's rising. It will move this way. The cooler, denser air from over the lake moves in underneath to take the place of that. And that is our sea breeze. Now, a land breeze is basically the same, but the opposite. This is usually what happens at night because we know that the water will retain the heat longer and the land will become cooler at night. So because at night the land is going to be cooler than the water, we're going to get a breeze coming off of the land. Winds are named from where they come, so this is a land breeze. So at night, the process is reversed. The land cools more quickly than the water, so the air over the land becomes cooler than the air over the water. As the warmer air over the water expands and rises, cooler air from the land moves beneath it, and that is called land breeze. So at night, the air over the water is actually warmer, and so the air over the water will rise. The cooler, denser air from the land will move in underneath it, and that gives us our land breeze. So that's basically the gist of it for local winds. And we definitely have local winds with being so close to Lake Michigan. They'll talk often about the lake effect snow or lake effect breeze and things like that. Here's pictures again that show that. You can see the sun shining on the land. The warm air rises above the land. The cooler air from the shore moves in. At night, it's the opposite. The air rises above the water because the water retains the heat. And the land then is cooler and the air moves off of that. Now, global winds. We're going to talk about some areas on the globe. Some of them have winds and some of them are less, we might call them like dead areas. And we're going to talk about them. And there's basically 5 areas that we're going to talk about. Global winds are winds that blow steadily from specific directions over long distances. Like local winds, global winds are created by unequal heating of Earth's surface. But unlike local winds, global winds occur over a large area. I'm going to grab a globe to show you. Okay. So a global wind would be like this. If the Earth was not spinning and if the Earth was not tilted, you can expect, and if the Earth wasn't spinning, you could expect that the air would rise at the equator, head towards the poles, cool, sink, and come back down. Okay? But because that is not the case, because the Earth is indeed spinning, we'll get a little bit. And as the Earth spins, the air moves this way, right? Okay. We're going to talk about how that changes the global wind patterns on the globe. Okay. So it says here, unlike local winds, global winds occur over a large area. Recall how the sun's radiation strikes Earth. In the middle of the day near the equator, the sun is almost directly overhead. The direct rays from the sun heats Earth's surface intensely, but near the poles, the sun's rays strike Earth's surface at a lower angle. The sun's energy is spread over a large area, so it heats the surface less. As a result, temperatures near the poles are much lower than they are near the equator. We knew that. Global convection currents. How do global winds develop? Well, temperature differences between the equator and the poles produce giant convection currents in the atmosphere. Local winds were smaller convection currents between the land and the sea, but global convection currents actually are basically cover the globe, okay? Warm air will rise at the equator and it will head towards the poles and it will sink there. And therefore, the air pressure tends to be lower near the poles and lower near the equator because the air is rising, and greater at the poles where it's sinking, okay? The difference in pressure causes wind at Earth's surface to blow from the poles towards the equator. Higher in the atmosphere, however, air flows away from the equator towards the poles. Those air movements produce global currents. So it will rise at the equator, head towards the poles where it will sink, and it will come back down because the air coming from the poles is more dense, it's colder. So it will come back down from the poles. There we go. So this difference in pressure causes wind at Earth's surface to blow from the poles towards the equator. Higher in the atmosphere, the air flows away from the equator towards the poles. Now, it would normally, like I said, just go up, come back down, up, come back down. But because Earth is spinning, we get these curves, and that's called the Coriolis effect. You can see that here. If the Earth did not rotate, global winds would blow in a straight line from the poles towards the equator. But because the Earth is rotating, global winds do not follow a straight path. As the winds blow, Earth rotates from the west to east underneath them, making them seem as if the winds have curved. The way Earth's rotation makes winds curve is called the Coriolis effect. So instead of it coming straight down because of the curve, because of the rotation, that wind will turn, and that is called the Coriolis effect. Okay? Because of the Coriolis effect, global winds in the northern hemisphere gradually turn towards the right. As figure 9 shows, a wind blowing toward the south gradually turns southwest. So if it's coming from the north and it's heading south, it will gradually turn southwest. And let me give you an idea here, closer to the United States, okay? As we come down, it will gradually turn to the southwest, towards like Mexico or Southern California. There we go. As figure 9 shows, a wind blowing toward the south gradually turns to southwest. In the southern hemisphere, it bends towards the left. So in the southern hemisphere, because it's coming from the poles towards the equator, it actually goes this way because it's moving from the poles towards the equator in that direction. So it's the opposite. I mean, it's really, they're both, that would be heading southwest, that would be heading northwest, okay? There we go. Now, global wind belts. The Coriolis effect and other factors combine to produce a pattern of calm areas and wind belts around the Earth, as shown in figure 11. The calm areas include the doldrums and the horse latitudes, which we'll talk about, and the major global wind belts are the trade winds, the polar easterlies, and the prevailing westerlies. The doldrums. Near the equator, the sun heats the surface so strongly that the warm air is just constantly rising. And if you remember, wind is horizontal movement. It is not up and down movement. So if at the equator the air is constantly rising, there's very little wind. So it's kind of like a dead area. If you were in a sailboat, you would not move very quickly through the equator because that air is rising. There's no wind being put in your sails. So near the equator, the sun heats the surface strongly. The warm air rises steadily, creating an area of low pressure. The cool air will move into the area, but is warmed so rapidly it rises before it moves very far. There is very little horizontal motion, so the winds near the equator are very weak. Regions near the equator with little or no wind are called the doldrums, meaning it's kind of boring, there's not a lot of happening. Now, so that is the equator. That is the doldrums. Okay. Now, the horse latitudes. Now, it's the wind that the air that rises at the equator doesn't actually make it all the way to the pole. It actually gets to about 30 degrees north up here, where it will cool and sink. Now, remember, again, this is sinking air. It's coming down. And so, therefore, again, it is not horizontal movement. Warm air that rises at the equator divides and flows both north and south. So, you'll have air going north and air going south. At about 30 degrees north and south, the air stops moving towards the poles and sinks. And in each of these regions, you'll find another belt of calm air. Calm, again, because it's not horizontal. The air is sinking there. It is an area of high pressure. It's coming down at 30 degrees north and 30 degrees south. Hundreds of years ago, sailors, because there was no wind, becalmed in these water, or meaning they were stuck in these waters, ran out of food and water for their horses and had to throw the horses overboard. Because of this, the latitude of 30 degrees north and 30 degrees south are the horse latitudes. I'm just going to write horse because area there is sinking and it's pretty there's not a lot of wind happening. Now, in between there, we get a lot of wind. So if it's rising at the doldrums, heading to the horse latitudes, it's coming back, it's going to be spinning this way, right? Because this wind, there's a lot of wind in between there. These areas are the trade winds. Let me read. When the cold air over the horse latitude sinks, it produces a region of high pressure. This high pressure causes surface winds to blow toward the equator and away from it. So it'll blow towards the equator and away from it. And I'm going to talk about that in a minute. The winds that blow toward the equator are turned west by the Coriolis effect. Okay? As a result, winds in the northern hemisphere between 30 degrees and the equator generally blow from the northeast to the southwest. Okay? In the southern hemisphere between 30 degrees and south latitude, the winds blow from the southeast to the northwest. Okay? And the wind, for hundreds of years, sailors relied on these winds to move ships carrying cargo around the world. They were really important winds. They would track and map these winds. They would carry cargo from Europe to West Indies and South America. As a result, these steady easterly winds are called the trade winds. Traders use them. We then have, above the 30 degrees north and south, we have the prevailing westerlies. In the mid-latitudes between 30 degrees north and 60 degrees north and south, winds that blow towards the poles are turned east by the Coriolis effect. So we have this sort of curving like this going around. The prevailing westerlies blow generally from the southwest in the north latitudes and in the northwest in the south latitudes. So they go like that and they go like that. Okay? Sort of that circle. Okay? The prevailing westerlies play an important weather in the weather of the United States. We are between those latitudes here in the United States. Okay? We are between 30 and 60. And so we get a lot of our winds coming up from the southwest here, which we saw today. A lot of our winds were south-southeast coming from that area. Okay? And then here we have our diagrams here showing you. So you can see again, just like I have, we have the doldrums in the middle. We have our trade winds heading towards the equator from 30 degrees north and 30 degrees south. Our prevailing westerlies heading in the opposite direction from 30 degrees north to 60 degrees north and 30 degrees south from 60 degrees south. And the last one we're going to talk about, and then we have the doldrums, which is the calm area rising, the horse latitudes where it's sinking. And the last one we're going to talk about is the polar easterlies. The polar easterlies. Cold air near the poles sinks and flows back toward lower latitudes. So at the poles, that air does sink and head back down, but it ends up sort of heading like this up here at the poles. You can see it heads this way, sort of more in just a general circle. Okay, the polar easterlies. Cold air near the poles sinks and flows back towards lower latitude. The Coriolis effect shifts these polar winds to the west, producing the polar easterlies. The polar easterlies meet the prevailing westerlies at about 60 degrees north and 60 degrees south latitudes along a region called the polar front. The mixing of the warm and cold air along the polar front has major effect on weather in the United States. That's where we get those polar vortexes and where the cooler moist air or the warm moist air and the cool dry air will dump a lot of snow. On top of that, in the United States, we have something called the jet streams. At about 10 kilometers above Earth's surface are bands of high-speed winds called the jet streams. I'm going to go over here, okay? And what happens is the winds blow only a few hundred kilometers wide, but the winds are a few hundreds of kilometers wide, but only a few hundred kilometers deep. The jet streams blow from the west to the east at speeds of 200 to 400 miles an hour. So if you're riding the jet stream on a plane, it can actually help propel your plane faster. This one will be colder. This one will be warmer, okay? As jet streams travel around the earth, they wander north and south along a wavy path. We'll continue to discuss these bands of wind in class. I hope that helps you out. We'll see you guys on the next reading.